Okay, so welcome to an introduction on embedded systems. This is part of the EECS3215 class, and this is session number 1. All right, so we're going to be talking today about what are embedded systems and what are the basic concepts behind them. So what's an embedded system? Well, basically, from an engineering perspective, it's this awesome piece of electronics that's programmed with fabulous software, and it allows you to work with all sorts of really interesting people in often other engineering or science domains, like in mechanical engineering or biomedical engineering or civil or aerospace applications. So it's a really important and integral part of a lot of good engineering projects. From the public's perspective, it's a really boring piece of electronics that they tend to ignore, and nobody really cares about until something goes wrong, because it's really expected to sit in the background and do its work. It's embedded there. You don't notice it. It does one or two or maybe three jobs really, really well all the time. 24 hours a day, 7 days a week, 365 days a year for many, many years, typically for an embedded system. So it's there, and it does its job, and when we do our job well, it does its job so well that nobody notices that it's actually there. What are examples of these mysterious embedded systems? Well, there are simple ones, like, for instance, the controller for a furnace, or the controller for an electric car window opener, or maybe the system that opens the automated doors at the mall, or shuts down an elevator in the case of an emergency. All sorts of industrial applications that you probably have never seen before, but are really important for making food or making components for other car parts or something like that. They're used in irrigation controllers. The next time you're butcher and you are getting your favorite salami, then when the butcher puts the salami on the scale and weighs it, the electronics inside of that scale that are calibrated, that are supposed to measure out to the nearest gram or portion of a gram, that's an embedded system. There are also really complicated ones, and they can be complicated for a variety of reasons. They can be technically complicated, they could be complicated from a regulation perspective, or they could be complicated from the perspective of social factors. And some of these would include, the latest rage, the Internet of Things, and they're supposed to be, within a few years, billions of these devices being made. There are things like insulin pumps. So that's a biomedical device. And so it would be complicated. The electronics might be simple, but the development of it could be really complicated because of the fact that it involves patient safety. Fitbits. There's an example of sort of a combination of Internet of Things and biomedical device all in one. Car engine controllers. So I know that electric car is the latest thing, but controlling a gasoline engine is actually a really complicated thing, and microcontrollers are really good at doing that sort of work. Vending machine controllers, making sure that you get the chocolate bar that you wanted and you get it for the right price, and that signals are sent back to the vending machine vendor for maintenance or resupply. That's really important. Another biomedical device, actually two of them, would be automated external defibrillators and artificial legs for amputees. Here's a typical example of one. I was skating the other day, and I looked around the change room and noticed a whole lot of different embedded systems in that room. So we were skating. We were at Dieppe Park, which is a City of Toronto park, and there's two ice rinks right there and there, and there's a building that has refrigeration systems in it, cleaning systems, and a change room. And in that change room, I saw the temperature sensor for the thermostat that connects into the furnace system or the climate control system. I saw a camera system, a security camera, probably an internet IP protocol kind of system. I saw an automated external defibrillator, which is basically a heart restarter. So if somebody has a heart attack, they get an arrhythmia in their heart, we can restart their heart. Saw one of those. That's an embedded system right there. I was in the washroom. I washed my hands, and there was the automated water turning off and on system. Okay, there's a sensor right in there. It's typically an infrared sensor, and it allows the tap to turn on and off. There was also the same sort of thing, but for the hand dryer. Finally, there was a sensor right over the door that automates the opening and closing of the door. These are all examples of automated systems, or sorry, embedded systems. And in this case, I easily found 1, 2, 3, 4, 5, 6 of them without even trying. Embedded systems are everywhere, and you don't notice them. And that's the beautiful thing about them. And so this course is all about making these things that, in the end, you think will be really cool and really interesting, but nobody else is going to give two figs about. Okay, but that's a good thing. All right, so in a lot of these embedded systems, you've got a chip, whether it's a field programmable gate array, an FPGA, or a microprocessor, a microcontroller that's involved. And what do these things sort of typically look like, or what are the specs on them? So back in the day, when I was a student, we used the HC11E9s. These were 8-bit microcontrollers, originally used in automotive applications, started about the 1985, 86 or so, and they were used well into sort of 2000. Okay, 8-bit, 8 megahertz. They had a couple of bytes of RAM. If you were lucky, you had some EEPROM, some 32K of EEPROM. It had communication ports on it for SPI, UARTs, SCIs. You would have some timers on board. That's always a really important thing with these microcontrollers. An analog to digital converter. There was no digital to analog converter the other way around to produce analog signals. No floating point capability in hardware. So it was integer-based math only. In terms of debugging, so trying to figure out what was going on if something went wrong, there was a serial monitor, so it'd send data over a serial link. Think of it like USB. And each chip cost in the neighborhood of $15 to $30. A development board would run you anywhere from $150 to $1,000. And they ran from about 1985 until about 2000 or so. A lot of us transitioned at that point to HC12s or S12 controllers, and that's what we find in the Dragon board. The chip itself, 16 bits, runs at 25 megahertz, has a lot more RAM in it. You can have E2PROM or flash memory as well. It has a bunch more communication channels, so SPI, UARTs, I2C, CAN bus, etc. That's automotive. Also has a lot of timers. All of these systems typically have timers, or you create timers for them. An analog to digital converter, a really big upgrade from 8-bit to 10-bit. Possible to have a digital to analog converter as well, so you could send analog signals out really easily. Again, no floating point capability in hardware. It was integer-based math only, unless you simulated or created software-based floating point. Debuggers in the form of a BDM. This was a big upgrade. It was really important. It allowed you to do a lot more good engineering development work without a lot of the guessing. The chips themselves cost in the neighborhood, that's not the development board, that's the chip, cost between $20 and $50 a piece. Used from about 2000 up until the present. The latest version is called the Magna V, and it's still being used in automotive applications. Really good, robust processor and lots of good peripherals on it. In our class, we use the Cyclone 2 FPGA, so it's not a microprocessor, it's similar to it. You can put a microprocessor into it. It can, on the board that we're using, it runs about 50 megahertz. It's got, the board itself has a lot of RAM. It can have some EEPROM or flash on board as well. The board that we're using has USB RS-232 Ethernet capability. There are no built-in timers. There is no built-in ADC, although you can add chips to make that happen. The board that we have has a DAC that allows you to produce VGA signals, but that's sort of an add-on. No hardware floating point built into the FPGA. You can program it using sort of a JTAG type USB blaster USB connection that's similar to the BDM that we had on the S12s. And the cost for the chip itself is anywhere between $150 and $190 from findchips.com. And the chip itself has been around since about 2005 to about the present. The latest version of the Cyclone is the Cyclone 10, and it's just been released. So these FPGAs are in constant development. If you're putting a new product into market, you might want to move to the Cyclone 10 instead of the Cyclone 2, but that's that family of chip. Starting about 2012, Freescale, then NXP, created the Kinetis version of an ARM processor based on the Cortex M0 Plus platform, designed to be a replacement for things like the S12 and the HC11 and other things like the AVR Atmega 8-bit processor, the 8051 as well. It's a fully 32-bit system, runs at about 50 megahertz or so, has it has 32K of RAM, it has flash as well, so 256 kilobytes of flash memory. It has a bunch of communication channels. Yes, there are timers built in. The ADC is an upgrade up to 16 bits. It has a 12-bit digital to analog converter. It again has no built-in floating point. In order to go and get on the Kinetis line of processors floating point, I think you have to go to the M4 Cortex chip. It has a built-in, not an external, but a built-in debugger system called OpenSDA, and you can get these chips for somewhere between, depending on which one you choose, $2.75 to about $7.50 based on the latest pricing from findchips.com. These have been around since about 2012, and they're used in all sorts of great applications, and you can get them with lots of features, with little features. You can get them with low latency, with really interesting sleep modes, things like that. And so these are typical kind of embedded chips that you can use in your embedded systems project. But really, there are thousands of these. And how do you go about choosing which chip to use in an embedded system? Well, it's important to point out that a lot of engineers pretend to be objective about this process, but it's really easy to be subjective based on how, it's hard to actually think about this with high cognitive load sometimes. We can be lazy, and so that can be a factor in the selection of which chip we end up using. And, switching from the thing you're familiar with to something better can be intimidating because you have to learn new tools and new techniques. So while we like to be objective, or we say that we're going to be, in a lot of cases when we choose these chips, we really are subjective about it. But it's important for you to think about this in terms of objective principles whenever possible. We tend to find that engineers and hobbyists tend to fall into camps of sort of one chip versus another chip, kind of like the Mac versus PC or Apple versus Android. We often see people debate the merits of PIC microcontrollers versus AVR microcontrollers. So AVR is the type of microcontroller that's used in Arduinos, for instance. And there's some really good links about the discussions that go on about that and how to be more objective about it. And I've pointed to two links right there from embedded.fm podcast and the EEV blog, the PIC versus AVR debate. That's a constant one. But the other one that we often have is should I use an FPGA or should I use a microcontroller? And that debate is one that we want to have in class. We want to have that discussion, and so I'll encourage a lot of that discussion because it's often not very clear, and there's a lot of subtlety involved. But for a good sort of baseline for how to be objective about that selection process, I point you to Jake Carlson's really interesting comparison of about 20-ish microcontrollers, and he based it on a starting point of the microcontroller had to be, or the chip itself had to be under $1 US, and he started from there, and he did a lot of testing based on what could you do for less than $1. And so I encourage you to go and take a look at that and see what he came up with. All right. And again, the internet is a fabulous place for resources on embedded systems. There are some really good resources like the Electrical Engineering Video Blog, EEV blog, run by Dave Jones. Do be careful. He can have a sort of coarse language, and so if you're not into that, then move on to something else. But I find them really interesting. There's the Embedded FM podcast, which I recently discovered, and it is wonderful. So it's audio only, so it's a really good thing to listen to on the bus or on the subway on your way to school. There's the Great Scott YouTube channel that's really good. The videos tend to be long, but they tend to be involved and demonstrate a lot of best practices in terms of soldering, in terms of programming, etc. And of course, there is the classic Circuit Seller magazine that has both an online component to it and like a paper version of the magazine. It's been around for a long time, and it's a really interesting magazine to read for embedded systems. Okay, so we're going to start off with a discussion of microcontrollers and FPGAs. So what is a microcontroller? Well, a microcontroller is effectively like an underpowered small version of the chip that's used inside of your personal computer. It contains a processor and it has some memory, but it also has other things like potentially debugging hardware like a BDM or a JTAG or OpenSDA. Often there'll be analog to digital converters or digital to analog converters, direct memory access or DMAs, serial ports. These could be like Ethernet, or they could be USB, RS-232, SPI, things like that, as well as parallel interfaces for memory and data and things along those lines. We do find that there's less and less of these parallel interfaces on microcontrollers because pins cost money, and so there's been a big push towards serial only lately. Examples of microcontrollers include the ARM Cortex M4 or M0 Plus, and you can get these from a multitude of vendors like TI or Freescale and XP. There's the 16-bit PIC24s and the 32-bit PIC32s, and these are from Microchip, which actually now owns AVR. You've got the 8051s, which are a classic 8-bit microprocessor in a variety of packages and capabilities by companies like Silicon Labs. And again, very capable. You can do a lot with these 8051s. Don't let the 8-bits fool you. You can do a lot of really interesting things with them. There's variants of the Intel 386 or the 386 processors that were around since about the mid-1980s, 1985 or so. They tend to be used in embedded systems because you can host an operating system, and they're relatively low power and pretty capable. And then finally, you've got the Arduino, which is typically run by an 8-bit AVR Atmega processor. And so these are examples of microcontroller type of systems or chips that you can use. All right. From there, what's an FPGA? So we're talking about microcontrollers and FPGAs in this course. An FPGA is a field programmable gate array. And effectively, it is a chip that has internal hardware, logic gates, inside that can change based on what you're trying to accomplish and how you program it. It's basically like a transformer toy, but in chip form. A really good discussion about what an FPGA is can be found on the Electronic Engineers video blog by Dave Jones, and the link to it is right there. It's EEV blog edition 496, What is an FPGA? So it runs for about 40 minutes or so. It's a really good overview of what an FPGA is. Why would we want to use an FPGA in an embedded system? Well, first, because they can be adapted. So they can be adapted in the customer's environment, or what we refer to as the field. They can be updated by the customer's technical person or technical department. They don't require the original vendor to make those changes for them. So that's a really good thing in a lot of cases. These are great for tasks that have a lot of parallel tasks or a lot of parallel data. And so like video applications are a really good example of why an FPGA is a good thing, because there's a little latency. The math that goes on in processing video typically isn't very complicated, but it has to be done very quickly and predictably. So FPGAs are a really good thing for that. They tend to be really good at replacing a lot of discrete logic components. So if you've got a lot of logic components, a lot of chips that are on your board, and you want to replace that with a single chip, FPGAs are a really good way to do that. Engineers often use FPGAs as they go towards application-specific ICs or ASICs. So an ASIC, when you design it and then manufacture it, can be really expensive. And in the process to get to that point, you often want to have a system that you can prototype and change and adapt and show your boss, and FPGAs are very good for that because they're relatively low cost when you compare it to the actual development of the ASIC. Often we will use them in conjunction with a microprocessor or microcontroller to offload parallel, data-intensive, quick tasks that are run in parallel, something that a microprocessor or microcontroller is really not good at doing without being really expensive and really capable. Why wouldn't you want to use an FPGA? Well, in a lot of cases, power consumption can be high. It tended to be that it was hard to add in analog subsystems into an FPGA, although that is changing now. And that in large volumes, ASICs and microcontrollers are just cheaper than an FPGA. FPGAs can run really expensive. So there are times where you should use them and times that you shouldn't. And a class like this is one where we can explore that design process. In the real world, there are good examples of why you would want to use FPGAs. One of them is software-defined radios, both at the hobby level and the professional commercial level as well. Oscilloscopes often have them in them because you want low latency, high bandwidth, parallel data to be processed using really simple math. And the Rigol DS1050E, I believe, I think I got a little typo there, or 1052E, is a really good example of that. You can actually see the Cyclone, I think it's a Cyclone 3 right there. Okay, and that's built into the oscilloscope. FLIR thermal cameras, so thermal cameras that can see sort of heat coming off of people or objects. They're good examples of applications where you would use an FPGA. You can simulate different microprocessors inside of an FPGA, and so there are times where you would want to do that as you're developing a microprocessor. And there are lots more examples in places like the forums for the Electronic Engineers video blog. All right, so now we're going to talk about some of the tools that are associated with doing embedded development, both hardware and software. So here you can see some boards that we use. These are the hardware things, and they're often programmed using USB cables. The software that you use often will be programmed in languages like C, but then you will disassemble it in order to examine how the program is written into memory on the microprocessor, and you'll use a debugger in order to examine sort of that disassembled version of the code or the C code via your USB cable. In EECS3215, we use FPGA boards. We use S12 or 9S12 boards like the Dragon board, and we use 32-bit microprocessor boards like the KL43Z from NXP. These are all example development boards. They're not something that you would typically want to sell to a customer after you've worked with it, but one that you would want to use as you're developing a system yourself. Get you up and ready really quickly. There are other examples as well. So, for instance, there are these microstick systems that allow you to program a 16-bit or 32-bit DIP socket package that can be inserted into an inexpensive processor board. There's the Teensy as well, the Teensy 3.1 that has an ARM Cortex M4 in it that is breadboardable as well. It's shaped like for a socket that you can put into a breadboard. Really easy, about $20 or so. There's the KL46Z, which is like the 43, just has more pins on it, more capability, more timers, etc. That's what that looks like. It's in an Arduino form factor. You've probably heard of Arduinos at this point. Arduinos come in a multitude of different shapes and sizes. In this case, this is like an Uno Arduino that has built-in Ethernet. This is an example of the KL43 board with a breadboard prototype on it, on top of it. This is it right here. There are proto boards or shields that you can get that plug into these Arduino boards. They're relatively inexpensive, easy to prototype with, often have the headers soldered on directly. So really good examples of things that you can get that are on the market right now. Things that we often don't talk about, though, are the debugger tools. And debugging is hugely important, especially when things go wrong. And so on the KL43 board, there's a built-in debugger that incorporates something called OpenSDA that allows you to access memory and things like that. For the PIC series of microcontrollers, there's something called the PIC Kit 3, which is about $30 or so, and that allows you to program directly onto the board. It's really good if you're going the PIC route. If you're using 9S12s or Kinetis, etc., there are the P&E Multilink, or there's another vendor called Sager that sells the J-Link. The J-Link can be bought for about $20 or so. And those are effectively replacements for the OpenSDA that you find directly on that board. So if you were to make your own board, you'd want to have one of these. But in our case, we've chosen a board that has it built in for free. So that's a really important thing. Now, you can also develop systems that don't have any of these, and you can go with a simple, tried and true, classic LED debugger tool and just flash your light with Morse code or something like that. Rudimentary, it works, but often you want to have one of these systems in order to do real engineering work using debuggers. Okay, so what you're going to learn about in this class is that design is often a compromise. And the decision to go either FPGA or microcontroller is sometimes an easy thing, especially if you've got things like massive parallel digital data. Doing simple math operations, that's often an FPGA choice. If you're doing a simple task over and over again, you want to have a cheap sub $1 microcontroller that can do that really easily for low power, low cost. That's a microcontroller task right there. But in many designs, you could go either way. And that would depend on cost, on the personnel that are involved, what their history, what their background is, what their expertise is, what their preferences are, as well as overlapping capability between sort of certain FPGAs and certain microcontrollers. That said, at the prototype stage, the costs for going FPGA or microcontroller tend to be about the same. Your software ID is typically free, so the software Verilog or C or whatever you're programming in, that thing used to cost a lot of money, and you can still buy specific software packages that are expensive, that have really good tools associated with them. There are good reasons for going that route, but typically as a third or fourth year engineering student, you go the free route, and you can get really good tools for that. Debuggers, if they're built into your board, like they are on these, for instance, they're free. Otherwise, you're paying $20, $200, $1,000 for those debuggers, depending on what you're trying to accomplish, how fast you need to program it, how much detail you need, etc. And you've got your hardware evaluation kits. So, the sort of boards that you're dealing with. So something like this, or the Altera board, like this. And those boards will run you anywhere from $10 for a little AVR type of 8-bit board to like $70 for an intro level FPGA board, to $1,000 or $5,000 depending on how much capability, what kind of chip you're using, etc. But as a third or fourth year engineering student, you can get away with spending less than $100 to get something that when I was a student I would have had to pay $5,000 for. So there's a lot of good capability for low cost right now. Now, when you go commercial, then there are other factors at play. Volume pricing, for instance. How much, if you're going to, how much will each chip cost if you buy 100,000 of them? That can vary. Lead time, is it going to take you 8 weeks or 2 years to get your chip from the vendor? I don't know. you'd have to find out, and that is often stated on the vendor's website. Product lifetime support. That is also really important when you're going commercial. So the chip that you're using for your class, well, we can change the course every year, and that's all right. But when you're creating a commercial product that you're going to be selling for 5 years, or you're going to sell for 2 years but have to support for 10 or 15 years with your customers, you need to know that you can replace those chips or have an upgrade path for them, a replacement path. And so product lifetime support from your chip vendor, that's important. And so you want to take a look at, with a PIC microprocessor, has it been around for a while, and is the vendor willing to support it for a long time? Have they stated that that development path for you? Or is the chip that you're about to choose slated for obsolescence and is listed on the website as not recommended for new design? Those are things that you want to consider. All right, all of this to say that this course 3215 is really for electrical computer software engineers, a preparation course for Capstone, which is the 4th year full year project course. You're going to learn some hands-on skills in terms of soldering, in terms of prototyping, in terms of selection of chip. You're going to learn about some project management, dealing with vendors. That's an important one. And you're going to get some experience with project-based rubrics or marking guides. Something that you'll often see in the Capstone class. It's a 4-level assessment process that's based on graduate attributes from the Canadian Engineering Accreditation Board, or ABET in the United States. We're typically aim to see that most students hit our meeting expectations level of performance in terms of the outcomes for the particular projects. So really you want to think of this course as one where you can explore embedded systems, but also one where you get some practice as to how you're going to deal with that 4th year engineering capstone class.